Okay, good afternoon. What's your question, Rodney?
Is it true that we get a retake?
So you guys are going to get an opportunity to retake one exam. And I will let you know when that is. All the exams will be completely different and new. You will have to tell me exactly which exam you want to take. If you tell me you want to take exam 1, that is the exam you can take. So you can look at your scores, see, you can replace one of your exams with this retake, but only one.
Are we doing it on Infinity?
It's going to be online. Okay. All right. Nate, you have a question?
I have a question too, Dr. Lott.
Yeah.
Okay. About the retake, and you said it's going to be online. Is it going to be on Blackboard or if
it's going to be on? I haven't decided yet. It's probably going to be on Blackboard, but I haven't decided yet. It may actually be on Xfinity, and what'll happen is you will write the exam on Xfinity or Blackboard, and then you will submit the exam within the allotted time. So you have to take a picture of it, submit the exam, and then I will look at the actual tests to see your work.
Okay.
Completed on the exam. Okay. Any other
Hey,
questions?
Dr. Lott, I just logged in. When is the makeup exam again?
I haven't decided yet. The reason why is because our last exam is the Thursday, the last day of class. And some people may want to choose exam 5 to be the exam that they make up. So it'll be sometime between exam 4 and exam 5. That's what I think I'm planning to do. Okay. All right. Any questions?
I had a question. We could still drop one of them, right?
Oh yeah, you're still going to drop one.
So you could drop one and make a one?
Yes.
All right. Thank you.
You're welcome.
We get to drop 1 exam, 2 quizzes, and 3 homeworks, right?
That is correct.
Okay, thank you.
Okay, any other questions? Can you guys see the Kahoot?
Yeah.
Okay, so in the last class, there was a question. People wanted to kind of know what the answers were to the Kahoot. So I wanted to just give you an idea of what the answers were. So for the first question, said Euler's method is used to solve, and the answer is both. You can solve a separable differential equation, and you can also solve a first order differential equation using Euler's method. The second one, we say an improper integral diverges when the answer is the limit goes to positive or negative infinity. All right, so that's the answer to that question. Number 3, a first order differential equation in standard form. Now, this is the one that got a few people. Okay, so you can definitely rule out the green one because it has an x squared in front of dy dx. We can definitely rule out the yellow one because it has an x in front of dy dx. Even though it has p of xy equals q of x, some people kind of got tripped up on that one. It also reads dx dy, so that one is definitely wrong. And the blue one is not in the right form, and so the only one that is in the right form is the red solution. And here, p of x is negative tangent of x and q of x is x squared. So that was the answer. To number 4, which of these numbers do not appear in Simpson's rule? The answer is 1. Simpson's rule is h over 3, so the 3 is included. And then the interior terms alternate 4, 2, 4, 2, 4. And so all 4, 3, and 2 appear in the formula. 1 is not actually visible, so that's not in the formula. True or false, the estimated error for the trapezoidal rule. Uh-oh, what happened here? I think I did something. There we go. The estimated error for the trapezoidal rule is smaller than the estimated error for the midpoint rule. That is false. The midpoint rule is smaller by a factor of 2. The midpoint rule is used to estimate the volume of revolution of a curve f of x, the area under a curve of a function f of x, the surface area of revolution of a curve f of x, or all of the above. It can do all of those because all of those are definite integrals. So the midpoint rule can be used to solve any definite integral. Okay. True or false, the comparison theorem is used to determine whether an improper integral is convergent. That is true. Next, an ordinary differential equation contains an independent variable x, a dependent variable y, and derivatives of x and y. That is false. It does not contain derivatives of x. Number 9, in a first order differential equation, y of x, the answer is the blue solution. Please note that that C must be included in the numerator. Okay, so it is the blue answer. And then the last question, the solution to the differential equation dy dx is equal to x over y. Y of 0 equals 1. That solution is a hyperbola. Okay, any questions? Johnny, you have your hand raised?
I had a quick question.
Yes.
So what if you get like let's say you get 100 on all the quizzes and you
Okay.
only need to drop one?
You have, this question has nothing to do with the Kahoot.
Oh,
Okay, so let me finish the Kahoot. I got you. I got your question. Okay, any questions about the Kahoot? Okay. All right.
Oh, I'm sorry. I just have one. Is it possible to go back and redo them after a certain period of time, like say 1 or 2 days later, or no?
To go back and do what?
The Kahoot to practice the questions again, or no?
I don't know. Now that I don't know. I guess it might be possible, but I've never tried that. So I really don't know the answer to that question. I'll have to look that up. Okay, Johnny, what's your question about getting 100 on all the quizzes?
so let's say you get 100 on all of them. You can't drop one. Can we replace that with something else?
You can't say that again?
Let's say you get 100 on all of them, like you pass them all, and
Oh, I know what you're saying. You got 100 on all the quizzes, and so there's no need in dropping one of those. Can you drop something else?
yeah,
No, you're dropping one test. What is it? One test? Now you got me confused. One test, 2 quizzes, 3 homeworks. Yes, I'm sorry, but that's what it is. Okay, any questions?
Is it possible to make up a test missed if we do have a medical excuse?
Everybody's going to get the opportunity to make up one test, and then they're dropping a test. That is plenty enough leeway. I'm telling you right now, there are professors who give you no slack. Okay, so you guys, it's but so much we can stretch this rubber band, okay? All righty.
Thank you.
You're welcome. I don't want inflated grades where people don't know the material because we threw away everything that you didn't know. So we have to.
I'll be fine with that.
No, Johnny, no. Okay, so let's go into sequences. All right, so a sequence, they're going to be in this section, we're going to be finding the formula for the general term of a sequence, calculating the limit of a sequence if it exists, and to determine the convergence or divergence of a given sequence. Okay, so the definition of a sequence. Here's the most important word. I'm going to highlight it. It is a list. It is separated by commas. Okay, so a sequence is a list of numbers like 252, 253, 254, 256, dot, 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 dot. That means a bunch of numbers in between. 503, 504, dot, dot, dot. It is an infinite list of numbers. Okay, so some examples: 1, 2, 3, 4, 5, dot, dot, dot. Okay, 1, 1/2, 1/4, 1/8, 1/16, dot, dot, dot. That means it keeps going. 1, -1, 1, -1, 1. It keeps going. Okay, so I want to, let's see here. Here we go. Slideshow. Okay, can everybody see the PowerPoint?
Yes.
All righty. Okay. What is the next number in the sequence?
8.
8. Okay, now if y'all didn't get that, I was kind of scared, but we're good. Okay. What is the next number in the sequence?
-1.
All righty. What's the next number in the sequence?
164.
Good. What's the next number in the sequence?
18.
How'd you get 18?
Oh, wait, hold up. My bad. I'm sorry.
21.
21.
21. Okay. Next number in the sequence.
6/7.
6/7. Next number in the sequence.
1/243.
Okay, very close.
It's gonna be negative, right?
It'll be negative.
1/243.
All right. Next number in the sequence.
23.
Right.
Awesome. Next number in the sequence.
1 something.
Oh, it is 1 something.
Oh, 164.
170.
170. Okay, next number in the sequence.
Is it 49 squares of 49?
No, but very close.
Is it 49 roots of 7?
49 is square root of 7. Okay. Next number in the sequence.
$128 over 17 something.
1701.
That's right. Okay, so here's the review. Next number in the sequence was 8. Phew, y'all got that. -1, 1/64, 21. What sequence is this?
Add the current number and the previous number.
Okay, yes, but this sequence has a special name. That is correct.
Fibonacci.
It's a Fibonacci sequence. Okay, good. Here's the sequence. 6/7. Okay. This sequence, each time we multiply by 1/3. Does anybody know what kind of sequence this is?
Geometry.
It is. It is a geometric sequence. Okay, what kind of sequence is this?
Does it start with an A?
It does.
Sound like aromatic?
Arithmetic.
Yeah.
Okay. And this sequence, there really is no special name for it. So you add 20, then you add 22, then you add 24, then you add 26, then you add 28. Okay, so for those of you who had not figured out what the pattern for this sequence is, you start by trying to find a common ratio or a common difference. Okay, this one, you just keep multiplying by the square root of 7. And this sequence, you keep multiplying by 2/3. Okay, any questions? All righty, we did that. We rocked that. We did that pretty well. So let me close my PowerPoint. All righty. Okay, so now we are back to our notes. Everybody looking at the OneNote sequences. And now we want to look at sequences in the sequence notation. So this sequence, which is n equals 1 to infinity, that tells what term is the first term and what term, where it goes. These are infinite sequences. This sequence, as you can see, if we look to get a pattern, I have 1, which is actually the square root of 1, 2, the square root of 2, the square root of 3, the square root of 4. The nth term in the sequence is the square root of n. Okay. The next sequence, b sub n, starts at n equals 1 to infinity. This sequence alternates. And as it alternates in negative, positive, it starts off 1, multiplies by 1/2, multiplies by, I'm sorry, negative half, multiplies by negative a half, multiplies by negative a half. And so the nth term of this sequence is -1 to the n minus 1 over 2 to the n minus 1. And this is a geometric sequence. Okay, the next sequence, this one was also in the PowerPoint. 0 over 1, 1 over 2, 2 over 3, 3 over 4, 4 over 5. And this one looks like n minus 1 over n. Okay, any questions?
You said the second one was geometric.
I said the second one was a geometric sequence, yes, because they all differ by a common ratio.
Okay, thank you.
You're welcome. Okay, so let me quickly catch up because I need to, these notes should be, I gotta keep my notes neat and in order. So we did the sequences, we did that. Oh. Okay. Next, here is the sequence notation. So if the sequence is a sequence AN, its elements in the sequence will be A1, A2, A3, A4. AN is the nth term and it will continue. If it's a sequence BN, you will see B1, B2, B3, CN, C1, C2, C3. So that is the form of how we're going to do our sequences. Okay, so now we want to talk about convergence and divergence of sequences. Okay, so I have some examples. Okay. All righty. So our first sequence we want to look at is AN, and it's n minus 1. This is the sequence above. And This sequence we're looking at is the nth term is the square root of n. Okay, and as we look at this sequence, we want to try to determine if this sequence converges or it diverges. So converges means when you converge on a site, that means all of you actually meet at a particular place. Okay, so convergence means to be able to meet at a particular location or a particular spot. Divergence can be in a number of different ways. Divergence can be that the numbers just go off to infinity, or divergence can be that the numbers oscillate back and forth and you just never settle on one place that they converge. So this first sequence is the square root of n. And as I look at this sequence, as you can see, as n gets really, really large, what happens to the nth term of the sequence? Anyone?
Isn't it getting smaller?
Okay, well, as n goes to infinity, what's happening to the square root of n?
The square root of n is also going to infinity, I believe.
Okay, so it's not going to get smaller. The square root of n is also going to go to infinity. Okay, so that says the 3 dots, which means therefore, that says an actually goes to infinity. So this sequence diverges. Okay, it just goes off to infinity and it never settles on any particular value. Okay. Okay, now let's look at number 2. That's Bn. And Bn is the sequence that is 1, -1/2, 1/4. Uh-oh, this one does not belong there. Okay. -1/8, 1/16. And this sequence, well, we kind of really can't tell. I know that the numbers are getting smaller, but they're still oscillating back and forth, positive to negative. So I'm going to try to draw this. All right, so we're going to try to draw this one. And so here is going to be, this is going to be my axis of, actually, I really don't want anything on that side. This is going to be my axis for n. And then I'm going to have an axis for b of n. Okay, so this is my axis for Bn. Okay, and so I can see n starts at 1, and when n is 1, I get that Bn is 1. And this needs to be extended just a wee bit longer. Okay. All right, now when n is 2, we get -1/2 or -1/2. So -1/2 would be somewhere around here. That's when n is 2. 1, 2. When n is 3, I'm at +1/4. So that is somewhere right here. And then when n is 4, I'm at -1/8. So that's here. And when n is 5, I'm at 1/16. So that's here. And I'm going to change to red because n is 6 is going to be there. n equals 7 is going to be there, n equals 8 is going to be there, n equals 9 is going to be there, n equals 10. Okay, so everybody gets an idea of what's happening. Okay, any questions? Okay, so just from this graphical diagram, can anybody give me an idea of what number they think that this sequence is converging to?
It's going to 0.
It's going to 0. Okay, so this sequence is indeed going to 0. Even though it's oscillating back and forth, it still gets closer and closer and closer to 0 with every next term in the sequence. Okay, so this sequence is trying really hard to go to 0. So I would say that the limit as n goes to infinity of the sequence Bn is actually 0. So now I'm using the word limit. What do I mean by that? Okay, so now we're going to take a ride back in time, and we're going back to calculus 1. Okay. Okay, so this is the definition of convergence. It reads, the sequence AN converges to the number L if for every epsilon greater than 0, there corresponds a n that an integer n that is also greater than 0, such that whenever little n is bigger than capital N, then the absolute value of a sub n minus L is less than epsilon. If no limit exists, then AN diverges. Okay, so to calculate the limit of a sequence, we just compute the limit as n approaches infinity of AN equals L. So I'm going to let you digest that for just a second. And okay, so I gave you an opportunity to write that down while I took roll. Now I just want to talk about it briefly. Hopefully your Calc 1 teacher explained this to you, but I'm going to explain it to you just a little bit right now. So I'm going to go back and steal my picture from the last example. So let's grab this picture. So what does this definition actually mean? So I can use this picture to help me. Okay, so recall for this one, Bn. So here we had a sequence Bn, and we said n goes from 1 to infinity. And we said that the limit as n approaches infinity of this sequence Bn was actually L. Okay, so if the limit of this sequence Bn is actually L, by this definition that says that given any epsilon greater than 0, I can find a number n such that if I'm bigger than that n, the difference between the sequence numbers and the limit is always less than epsilon. So let's just take for a moment this last piece, and I have the absolute value of b sub n minus L is less than epsilon. So that means negative epsilon is less than Bn minus L, which is less than epsilon. So that then says that L minus epsilon is less than Bn is less than L plus epsilon. Okay, so we said for this problem, L was 0. So we said the limit was 0. So now I need to get a value of epsilon. So whatever epsilon is, and I can write here L plus epsilon, and I can write here L minus epsilon. So that's the little epsilon window that I'm talking about. That's that region. And I can look at all the values that are within L plus epsilon and L minus epsilon. So for that very large epsilon, because that epsilon is very large, you can see that after n equals 3, right here, after n equals 3 and on, all the rest of the values are inside this window. So all the rest of the values are inside here. Okay, as you can see, all the points are inside there. Now, what I can then do is choose a smaller epsilon. So if I choose a smaller epsilon, let's say L plus epsilon here, and L minus epsilon here, and I draw a line like this, and I draw a line like this. You can see now I have to go all the way up to n equals 4 before all the points are inside that little region. So every time I make my region a little smaller, I'm going to have to go further out in the sequence to get all the points inside of there. That's what it means for the limit to exist. Now, obviously, if the points are getting bigger like that, then I'll never be able to squeeze them inside of something. Okay, and if they're oscillating, so that if they're oscillating like that, or if they're just getting bigger, I should have said that, if that's bigger, then you'll see then that that's when we don't have a limit. Okay. So that's the graphical picture of it. So now what do? Well, you just take the limit of the sequence. Okay. So here's some examples. All right, so number 1, I will let AN be the sequence 1 to infinity, be the sequence -1, -1/2, -1, -1, -1/2, -1/3, -1/4, -1/5, dot, dot, dot. So what I need you to do is tell me the form of AN. So we need to be able to figure out what's the pattern for AN. Well, A1 is -1. A2 is -1/2. A3 is -1/3. A4 is -1/4. So now that I've looked at that, I think I can go back and put a 1 under here. And so now I have that. So can anybody tell me what AN equals?
Is it just -1/n?
It is -1/n. Fantastic. Thank you very much. Okay, so now we know what the nth term looks like. Okay, so I can go back up here I can put in -1 over n. Then I can put in ... because this is what the nth term of the sequence is. All right, so now to determine if this sequence converges or diverges, all I need to do is to take the limit as n approaches infinity of -1 over n. Now, I'm going to go over some limit laws just to refresh your memory. But if you do recall, if I have a number inside, I can pull that out. So I can pull out the -1 and make it the limit as n approaches infinity of 1 over n. Okay, now we've talked about this limit before. All right, we said that anytime an n or something in the denominator is getting larger and larger and larger, and the numerator stays fixed, that's like taking one pizza and dividing it by everybody on campus and then choosing to include more institutions. The amount of pizza that you're going to get is going to be so small, it's almost nil, which is 0. Okay, so this limit is -1 times 0. So this is 0. So now we know this sequence converges. So the sequence AN converges to capital L, its limit being 0. Any questions about that?
Can you explain that again?
Okay. What kind of give me an idea of where to start?
We were talking about the limit.
Okay. All right. So just like this picture back here, where we were trying to see where the numbers go. So the numbers were here, and then it got here, and then it got here, and then it got there, and then it got here, and then it got there, and then it got here, and then it got there. And so you could see that those numbers were converging to 0 because that is the value of the height. So we do the same thing, but we're doing it analytically. So that means now we're going to actually take the limit. And anytime the denominator is getting bigger, the bigger the denominator, the smaller the fraction. The bigger the denominator gets bigger and bigger, the fraction gets smaller. Well, if the denominator is going to infinity, eventually you have a number over something that's so big that the result of the ratio of 1 over basically something going to infinity itself is 0. Okay, so I will say something about this in a minute, but we need to remember and keep in our minds that the limit as n goes to infinity of 1 over n is 0. We're going to need that. Okay. Did that help?
Yes.
Okay. That was pretty cool. Yeah. All righty. All right, number 2. Going to take a BN. And BN, oh, we're going to do that sequence we had before. 0, 1 over 2.
Like that.
Actually, let me do a different one.
Will it be harder?
No. 2 over 4, 4 over 6, 6 over 8, 8 over 10. Oh, well, for crying out loud, I may as well do the other one. That's just twice the other one. It doesn't matter. I may as well do the one I had. 1/2, that's twice the other one. They all just gonna reduce.
Yep.
2/3, 3/4, 4/5. And yes, that's right. Okay. So the nth term of this sequence, what is the nth term of this sequence? Well, let's see. This is how we figure it out. We say that first off, we have B1 is 0. B2 is 1/2. B3 is 2/3. B4 is 3/4. And we can keep going. So if we go back, it looks like this, if I put a 1 under here, that does work. So now I have B1 and a 1, I have B2 and a 2, B3 and a 3, B4 and a 4. So I can get that Bn clearly is going to have an n in the denominator, and the number above it is always 1 less. So there's the form of my Bn. Okay, any questions?
Just like that?
That's the form of it, yes. So the sequence Bn is always n-1/n, and I'm assuming that's the nth term where n starts at 1 and it goes to infinity. So this is 1 to infinity. So I can go back in here and put in n-1/n, comma, dot, dot, dot. Okay, any questions? Okay, now let's see if this thing converges or not. So the limit as n approaches infinity of Bn is the limit as n approaches infinity of n-1/n. And first pass, I get infinity over infinity. Whoa. That's one way of doing it. Or, and then we could use L'Hopital's rule. But an actual easier way to do this would be the limit as n approaches infinity, and just use algebra of Bn is the limit as n approaches infinity. I can make it 1 minus 1/n if I just split the fraction. And we know 1/n, we just said, goes to 0. So this limit is 0. So therefore, the sequence, that is not 0, that is 1. I apologize, my brain just slipped for a moment. That is 1. Woo, glad I caught that. Sequence Bn converges to L equal to 1. Okay, any questions so far? Okay, so we're going to take a break and talk about limit rules. Okay. So we want to do some limit rules. Again, these should be review. So we're going to let AN and BN be sequences. And AN is the sequence that converges to capital A. which is a real number, and Bn is a sequence that converges to capital B, which is also a real number. All right, then the following things are true. There's a lot of them, but one, it's review, and two, I'm posting the notes, so don't panic. And we do these without thinking about it. In fact, we've done it already. So the sum rule says, suppose I'm taking the limit of the sum of two sequences, then the answer is just the sum of the limits. Okay, so you can do the limit of an is a plus the limit of bn is b. So you get the sum of the limits. The difference rule. The limit is an of an minus bn. Again, you take the limit of an, which you get a, minus the limit of bn, you get b. Okay. The constant multiple rule. So if k is a real number and it's multiplying, I can just find what the limit of the sequence and then multiply by k at the end. Okay, and I did that already with this one up here. I found the limit of the sequence was the limit of 1 over n was 0, and then I multiplied by the -1. So I already used that rule and we didn't even think about it. The product rule, the limit of the product of two sequences is just the product of the limits. The quotient rule, assuming that b is not equal to 0, or the denominator, the limit of, as n approaches infinity, of an over bn is just limit of the quotient is the quotient of the limits. Okay. And then the power rule, if I have a limit raised to, I'm taking the limit of something to the p power, then that's the same as taking the limit to the p power. And then what I call the denominator rule is just what we said. The limit as n approaches infinity of 1 over n is 0. Must be committed to memory. Okay. Examples. Number 1. An is the sequence whose nth term is 4n minus 3 over 5 minus 6n. Okay. So please take the limit of that and tell me what you get.
Is 5.1 going to be on the test?
Yes. Yes. While you're computing that limit, I will go through that. Your exam will cover section 3.6, numerical integration. Section 3.7, improper integrals. Section 4.2, numerical methods. Section 4.3, separable differential equations. Section 4.5, first order linear differential equations. Section 5.1, sequences. And it is possible it may cover 5.2. Okay. I love that y'all ask questions. Okay. What's the answer to this limit? I know we went back, I know we've gone back literally almost a whole 2 semesters because we're almost at the end of Calculus 2, and this is taught at the beginning of Calculus 1. How do you compute this limit?
Can you re-show me how to do it?
Okay, all right, so we're going to take the limit as n approaches infinity of 4n minus 3 divided by 5 minus 6n. And if I put n in the numerator, I get positive infinity. And if I put n in the denominator, I get negative infinity. And so therefore, that's infinity over infinity. So I can use what property or whose rule?
L'Hopital's rule.
I can use L'Hopital's rule. So I'm going to take the derivative of the numerator. That's just 4. And the derivative of the denominator, that's just negative 6. So that's negative 2/3. So eventually all of the items, all of the elements in this particular sequence will start to look like negative 2/3. Okay, so the limit as n approaches infinity of a sub n negative 2/3. Okay, the next one is a little more challenging. It is the sequence, the cosine of n pi over 2. Now we know what happens with the cosine function. The cosine function oscillates, okay? So we kind of have an idea of what this might look like, but we're going to actually go ahead and find some values because you can't just take the limit as n approaches infinity of the cosine of n pi over 2, because that becomes the cosine of infinity, and we don't know what that is. So that doesn't make any sense to us. So that's not useful. Okay, not useful at all. So I'm going to draw a table. So we only draw a table when we have things that we're not sure of. Otherwise, we don't draw a table, and just finding values is not going to be an answer to a problem on the exam. So if you just find 5 values and then give me the 5th value, that's not going to be an answer. Okay, you have to be able to use whatever it is that you're working with to come up with an answer. Okay, so here's n. This is going to be n pi over 2. And this is going to be the cosine of n pi over 2. So I'm going to start off n equals 1, n equals 2, 3, 4, 5, 6. Hopefully, maybe by I should have an idea by then. So this is going to be pi over 2. This is going to be pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Okay, so the cosine of pi over 2 is 0. The cosine of pi is -1. The cosine of 3 pi over 2 is 0, but the cosine of 2 pi is 1. The cosine of 5 pi over 2 is 0. The cosine of 3 pi is -1. The cosine of 7 pi over 2 is 0, and the cosine of 4 pi is 1. Okay, so now I know that this thing Bn looks like 0, -1, 0, 1, 0, -1, 0, 1, ... Okay, so does that look to you like it is converging on any one value?
No.
No. Okay. All right, so this sequence is just oscillating up and down. Okay, goes 0, -1, 0, 1, then it goes, okay. So we can say the limit as n approaches infinity of the sequence Bn does not exist. Okay, so that lets us know there are some sequences that just don't have limits. Okay, so here's a tough one. Cn -1 to the n of n minus 1 over n. Okay. All right, so we've already done the one where we didn't have this. So we've done that sequence. And what did we say that sequence converged to?
Zero. Wait.
No, not quite.
Yes.
There it is. I called it Bn earlier. And Bn, we looked at these numbers and they're getting closer and closer to 1 because the number in the numerator is always 1 less than the denominator. So for example, a number in this sequence might be 999,000. Oh, that's not what I want. 999,999 divided by 1,000,000. That number is really close to 1. It is 0.99999. Okay, so these numbers are getting closer and closer and closer to 1. Okay, so this happens to be a number in the sequence. All right, so let's go back to the problem we're working on. And what's different with Cn? So Cn has -1 to the n. Okay, let's see what this looks like. So when we write it out, I think I'm going to make it -1 to the n. That's fine. Okay, so the sequence Cn, oh no, almost out of time. The sequence Cn, we're having so much fun. The sequence Cn, so we start off with 0. And then the next one, which is the second one, should be positive. So that should be 1 over 2. And then -2 over 3. and then positive 3/4, and then negative 4/5, and then positive 5/6, and then negative 6/7, etc. Okay. So now, if you look at this sequence, and that is not right. Oh, yes, it is. It just looks weird. Maybe I'll make it n-1, and then it won't look so weird. So this one's negative, this one's negative, this one's negative. Okay, now it doesn't look so weird. Okay, so as we're plotting this, you should see, this is what you'll see. So you'll see something that looks like this. All right, so the first term, when n is 1, which is not there, when n is 1 is at 0. Then it goes to -1/2. And then it goes to positive 2/3. Then it goes to -3/4. And then it goes to positive 4/5. And then it goes to -5/6. And then it goes to positive 6/7. Okay, so what you're going to see is these numbers are trying to approach +1, where these numbers are trying to approach -1. So this sequence diverges. Okay. So let's do some commonly occurring limits. I didn't realize we were running out of time. These we need to know. Uh-oh. All righty, so number 1, we already said this one. The limit as n approaches infinity of 1/n is 0. There's nothing you can do but memorize that. Okay, the next one, the limit as n approaches infinity of the natural log of n over n. This is also 0. Because n grows faster than its natural logarithm. 3, the limit as n approaches infinity of x to the 1/n is equal to 1. And this is true if x is greater than 0. You may also see it as the limit as n approaches infinity of the nth root of x. Okay, this is also 1. Number 4, the limit as n approaches infinity of 1 plus x over n to the n is e to the x. Again, most of these you can prove using, you can prove all of these actually using some form of L'Hopital's rule. 5, the limit as n approaches infinity of n to the 1/n is 1, or you may see it as the limit as n approaches infinity of the nth root of n. It may show up in problems both ways. Number 6, the limit as n approaches infinity of x to the n is 0 if the absolute value of x is less than 1. Number 7, the limit as n approaches infinity of any number to the n over n factorial is 0. Okay, so these are our common limits. Please commit them to the amazing list of other things that you need to commit to memory. Okay, so I have 4 minutes, so let's do some quick examples. And these are quick. So number 1, if a sub n is equal to the natural log of n squared over n, and I want to find the limit of that sequence, I can write this, I can bring the 2 down and write this as the natural log of n over n. So therefore the limit as n approaches infinity of an is the same as the limit as n approaches infinity of 2 times the natural log of n over n. But that's 2 times, this limit goes to 0. So that limit is 0. Number 2. Bn is equal to the nth root of n squared. Well, I can write that as the nth root of n squared. So therefore the limit as n approaches infinity of Bn is the limit as n approaches infinity of the nth root of n squared. But the nth root of n goes to 1, so that's 1 squared. So that's just 1. And number 3. So Cn is equal to n minus 2 over n to the n power. And I can write that as 1 minus 2 over n to the n power. And so now I'm going to use this property, number 4. So I get the limit as n approaches infinity of Cn is the limit as n approaches infinity of 1 minus 2 over n to the n power. And here the x is -2. So that's e to the -2. Okay, when we start on Monday, we are going to be looking at the sandwich theorem. We have a few more limits that we need to compute. Some of them are really tough. You will see the limits get more difficult, but you just have to remember, just rely on your knowledge from Calc 1. You've already done all these limits. Okay, so this is just a limit revisited in order to calculate the limit of a sequence, that is, where is the nth term going? Okay, so this is it for today's lecture. Are there any questions? Okay, all right, then I will see you guys on Monday.